Good afternoon, everyone. I'm Sumei Liu, a chemical oceanographer and the host of today's seminar, the Future Ocean Forum. So it's our great pleasure to welcome Professor Jacob Carlsson from Aarhus University, Denmark. Now I briefly introduce Jacob. He is a professor at Aarhus University, Denmark, and earned his master and postdoc degree from Technical University of Denmark. His research is marine ecology. It's very broad area, including nutrient dynamics, phytoplankton, hypoxia, and ocean acidification, and environmental management. He is a very well-known scientist, demonstrated by H index of 70 and over 20,000 citations, and highly cited researcher. In 2023, the award, I don't know how to pronounce because there are some text on the letters. Okay. Okay. And the presentation Jacob will give is about eutrophication and oligotrophication. So now Jacob will presentation. Okay.
Okay, so we start with this one. Okay, so the other one ran out of battery. Okay, so the first signs of eutrophication were actually discovered or coastal eutrophication were actually discovered by one of my former colleagues. He's retired now, Björn, and this is back from the 70s. So he was a student of the famous Steeman Nielsen. He was an oceanographer. He's the person who actually invented the carbon-14 method to measure primary production. And what Steeman Nielsen had done, he had looked into the primary production in the open waters, you could say the Danish Straits that's connecting the Baltic Sea with the North Sea. And this is showing his results from 53 to 57. And then his student, which was, you could say, one of my mentors, Gunnar, he did the same in 75. And these are the measurements that he found in 75. And he said, something has happened. Suddenly, the primary production has almost doubled over these 2 decades. There's something, this is, you could say, raising a flag of concern. We have to think about what are the consequences of this. But still, this was not really recognized by people at this time in the 70s. Actually, people thought that, well, the sea is vast. You could say it doesn't really matter what we throw into the sea, it'll disappear. There was this English movie that was called The Cruel Sea. In Danish, this was translated into something more literally, that the sea will remove all traces. So this was basically the paradigm. This was the understanding that in those days that you can just send out everything, all pollution, everything, you could say, whether it were chemicals, whether it was nutrients, whatever, it doesn't matter. If you put it out to sea, it'll be gone, it'll disappear. Like the Brits, there's this in the UK, in England and Scotland and Wales and Ireland, they had this thought to say, well, the solution to pollution is dilution. That's what they said about it. And they didn't recognize that it had some consequences. But it did. And in the 80s, we realized something was really worrying in the marine environment. One of the first cases was actually from a chemical factory on the west coast of Denmark. They had buried, you could say, really toxic materials in the sand dunes. And fishermen realized, you could say, that the fish that the fish they died and the fish that they got, they got sick of eating them. So suddenly there was an environmental problem. So this was just one of the first signs that, we really have to take care of, what we do. Second was in 1981. This is the first real, you could say, extensive recording of hypoxia in Danish waters. As you can see, you could say from this drawing, this is where people, or at least you could say some people thought this is where it's happening. This is not very accurate. This is just like more or less hand drawn. Say we think this is where people have, you could say, some reports of maybe dead fish or something else. So we probably have some hypoxia in these places. But this also led to the first action plan on reducing nitrogen, phosphorus, and organic matter inputs to marine waters. Later on, in 1986, we had the first real massive oxygen depletion, or you could say hypoxia event happening. It was actually fishermen in the northern part of Zealand, so not so far away from Copenhagen. They were coming with catches of dead lobster. So all the lobsters that they had in the nets were just dead. They were dragging dead lobster out of the waters. And this led to a public outcry saying, now this has come too far. We need to do something about it. So this was the first, after this, the first national aquatic action plan was actually enacted. But it was not the last one. About 10 years later, we had collapse of an estuary. It was called Maria Fjord. It actually went, and you can see that from this figure down here. So these are the oxygen concentrations, and this is the depth profile, and this is over the year 1997. Normally, this estuary has a strong stratification, and it's hypoxic in the deep layers. But what we could see that over the summer period, it actually, all the hypoxic water or the anoxic water went all the way to the surface. So it became completely anoxic from the bottom to the surface. And the smell around this whole estuary was just terrible. You have the smell of hydrogen sulfide everywhere. So people were outraged about this. And you could find, this is a picture from this period, you could find eel that were actually trying to escape the water. They would try to crawl on land because this could make them breathe, because they couldn't find any oxygen in the water. And just a few years later, in 2002, we had the worst ever recorded hypoxia, or event of hypoxia. So we had almost 9,000 square kilometers covered by less than 2 milligrams per liter, or affected by less than 2 milligrams per liter. A lot of recordings everywhere along the beaches or along the coastline of dead fishes walking ashore. And just to put it into perspective, this 9,000 square kilometers, it's about the same size as, you could say, the hypoxic area you have off the Mississippi River in the Gulf of Mexico. And it's also similar to what you have off the Changjiang River estuary in the East China Sea. It's also around, you could say, 9 or 10,000 square kilometers every year. So this was exceptional, though. In the old days, we did have some, you could say, the first, you could say, action plans were done on a very, you could say, very simple scientific basis. There were some studies already from early 90s. So this was one of them showing that normally if you have the more people that live in the catchment, the more export you have of nitrogen. Of course, today we take that as granted, this is natural, but in those days, this was not really realized. So this was sort of the very basic understanding. The more people live in the watershed, the more nutrients being exported. Okay. And also, the more nutrients are being exported, the higher primary production. So this is work from Scott Nixon. So this was sort of the understanding of it. And there was also the understanding that if we increase the input of nutrients to our system, we will have an increase in primary production. But if we reduce the nutrient inputs, we will also have a similar decrease in primary production and all the associated consequences. So we can reverse eutrophication. This is the idea behind many of the action plans that have happened. I've already now put the timeline in here. So now we are a little above 6 million people in Denmark. That's probably similar, I imagine, to Qingdao, maybe. I'm not sure how many people live in Qingdao. We've had 10 million, so a little bit less in Denmark. So we have the National Action Plan, the one that I just mentioned, and more recently we have the European directives going in to regulate nutrient inputs. We have the Water Framework Directive that you might have heard of, and also the Marine Strategy Framework Directive. So these are framework directives that gives us the possibility to manage, you could say, land-based sources to ensure that we have good ecological and environmental status in our coastal waters. This is a graph showing what the nitrogen input has been to, from land to coastal waters in Denmark. The old time series is something that I reconstructed, you could say, from having, you could say, some inputs on how many people lived and if they were connected with sewers, etc. And also the diffuse sources is based on freshwater discharge and establishing a relationship between nitrogen input and freshwater discharge for diffuse sources. In more recent years, since 1990s, these are very accurate estimations. And as you can see here, we've had an increase from maybe around 20,000 tons per year up to over 100,000 in the worst years, tons of nitrogen coming out, from land to coastal waters. And since then, we have managed to reduce the nitrogen inputs and nitrogen and phosphorus inputs a lot. We've actually reduced phosphorus input by more than 90% and nitrogen inputs by about 50% since the 1980s. All this was done due to an adaptive management scheme. Basically, it goes on, do we have a problem? Yes, we have. Set up a plan, make some action for it, check to see are we complying. So this involves monitoring and evaluate, do we meet the goals that were established? So especially this one, this was the adaptive scheme, checking that are we actually reaching the reduction targets that we were aiming at? And if not, we need to do something else. We need to do something in addition. And these nutrient reduction management plans have actually been quite successful, especially for point sources. So here, this is the TN input or total nitrogen input from point sources. You can see that throughout the whole period, urban sewage water or sewage treatment, what's coming from urban wastewater treatment plants is the major source, but that has decreased a lot. We also have from industry, from aquaculture, from overflows, and also from some scattered sources. Scattered sources are just like people living on the countryside that are not connected to sewers. And as you can see, overall, the decrease from the earliest, you could say, really detailed partitioning of all these different sources from 89 and until now, it's gone from more than 25,000 to around 5,000 tons that's coming from point sources. So that has been successful. Addressing point sources has been extremely successful. Diffuse sources are a little bit more difficult, but still, we have managed to actually reduce those quite drastically, at least quite, you could say, considerable. What this graph is showing is that for every year, we have sort of, it's a nutrient budget for the agriculture, for the diffuse sources. So we have some inputs and we have some outputs. So if we just start with a simple one, that's the output, that's the harvest. So here we can see the yellow ones, that's showing the amount of nitrogen that's been exported from the agriculture sector in terms of, you could say, crop yield, you know, what they harvest, and also production of pigs, etc. So, and any kind of meat animal production that's happening. And the sources we have here, that's the red ones are atmospheric deposition. We also have some nitrogen fixation because some plants can fix nitrogen. So that's bringing nitrogen also to the field. We have sludge and sewage. So some of the sludge that's being produced at sewage treatment plant is being, you could say, redeployed or put back onto the field to agriculture. And then sow seed, that's basically nothing. You know, the amount of nitrogen that you use in the seeds, you cannot even see it here in the graph. It's so little. We have animal fertilizers and we have chemical fertilizers. And as you can see, most of the reductions have been in the chemical fertilizers. But what's important is that if you look at the total nitrogen input, so that has decreased over time, but at the same time, you have maintained the same output in terms of crop yield, which is actually just optimizing your nitrogen use within agriculture. So the nitrogen balance shows the amount, that's the difference between input and output. It just means that basically we're still producing the same amount just for putting less nitrogen into the whole system. These are just different plots showing more or less the same. So if you look at the total nitrogen input, so this is both from point sources and diffuse sources, you can see that diffuse sources is the major part of all the nitrogen that's coming in. And here it's as a total, and here it's just listed as in kilogram nitrogen per hectare. And if you also look at the, you say the TN concentration for different sources, you can see that the TN concentration discharging from arable land, that has declined. If you have the TN inputs from aquaculture, the concentration of that have also declined. We have natural areas which are much lower. So these are the concentrations from forested areas that are not affected by agriculture. Those are also low. So if we look into what's happening then in the marine environment, I would say in the beginning, we actually thought this was going the right direction. We can see that here from the 19, this is the chlorophyll, the annual mean chlorophyll concentration in estuaries and coastal waters. And if you end by somewhere here in the 2013, one might have imagined that, okay, there is decline, we've been successful. But over the last 10 years or so, it's gone the wrong way. Things have really worsened again. And this is still a little bit puzzling. And especially if you look into this graph here. So this is showing the amount of chlorophyll versus total nitrogen concentration. So again, you could say across, you could say as an annual mean for all these estuaries and coastal waters that we have. But we can see that chlorophyll A, the amount of chlorophyll relative to the total nitrogen concentration is increasing, and it's increasing almost by a factor of 2. So apparently phytoplankton is becoming a lot more efficient in utilizing the nitrogen that's available in the system. My thoughts, and I'm still working on sorting that out, is that this has something to do with climate change due to increasing turnover of nutrients. We have warmer waters, especially in winter period, where we see the increases mainly in the winter period. So where we did not, in the past, did not have much winter production, now we are seeing more and more production happening in the winter, whereas we still have high productivity in summer as well. So, and especially the last 10 years, temperatures have really risen drastically. So the natural culprit of these changes, that's the warming that we see. Anyway, I want to return to something. This is the monitoring program that we have, just to show you that we actually have this very extensive monitoring program in Denmark. This is a plot of stations that we have divided into. These are North Sea, Skagerrak. So this is more oceanic or high salinity areas. We have the red ones here are what we call coastal waters and estuaries. And then we have the open waters in the Danish Strait. So this is where we're connecting. This is the Baltic Sea we have here. This is the North Sea. And this is the transition area between the two seas that we have. This is quite many stations that we have. I think it's still a very good monitoring program we have, even though it's reduced and under scrutiny. So unfortunately, we are receiving reductions in the funding for this every year. Anyhow, most of these stations, or many of the stations, are being monitored every 14 days. So 24, I would say it's officially called 24 times per year. So this does give us quite an amount of data to actually say something about it. If we look at DIN and concentrations in the two different categories, we can, there we go. We can see that if we start here in the more, you could say, in the systems that are closer, more connected to land, estuaries and coastal waters, we could see this clear response in the beginning. This is a clear response of the nutrient reduction or the nutrient management that we had. So nutrient concentrations really dropped down. And then since early 2000 have more or less remained constant. The effect in the open waters here is less. So here we saw an effect in the beginning decreasing, and then it has more or less stabilized. But the change is not so drastic in the open waters as it is in estuaries and coastal waters. And if we look at the DIN concentration versus discharge, so the first line up here, this is before you could say we were really addressing diffuse. There was this very intimate relationship between the freshwater discharge and the concentrations that we're seeing. But since then, every year, these annual means have just dropped down further and further away from this line, indicating that these nutrient reductions were actually effective. And you can see that 2024, which is the last year we compiled, it's all the way down here. It was a very wet year. It was the wettest on record. The thing with is actually increased precipitation. And with increased precipitation, we also have increased freshwater discharge. So this is the annual freshwater discharge over the years. And you can see that there's a significant increase over time. So our climate is becoming wetter and wetter. This means that more and more water needs to, you could say, drain all the arable soils. And you could say they bring a lot more nutrients with them to the sea. So another aspect of climate change that's affecting it. So if we look at nutrient concentrations, let's start with that. Here, this is just showing more or less repeating that when we look at total nitrogen, we could also see in coastal waters and estuaries, we could see a clear effect of the nutrient management. 800 down to more 400, between 400 and 500. And we also saw a smaller decrease in open coastal waters. But total phosphorus also clear. Maybe I should not comment so much, but we had a little bit of an issue here in these orange or these gray boxes with the measurement of total nitrogen and total phosphorus. So those annual means should be taken with a little bit of caution, but they might be off by something on the order of 5 to 10%. But so it's not really changing the picture drastically. At the chlorophyll concentrations, both in estuaries and coastal waters, it had this drop down and then an increase in recent years. It looked like, something similar was also happening in the open waters. There might have been a slight decrease here, but when we look at the last 10, 15 years, we see an increase again in chlorophyll. And if we look at second depth, there was improvement in the beginning, but in the last 10 years, we've seen a worsening. So what we thought to be really a success story 10 years ago have turned into the opposite now, even though that we haven't really increased the nutrient inputs. We maintain the same nutrient input, but something else is moving in the system. So one of the earlier studies that I was involved in, this is what we termed the Neverland story. It's a very well-cited paper. Carlos Duarte was the first author of that one. And sort of the basic tenet of this was that that you cannot return a system to its starting point. So basically, that a system remains, you could say, more or less unchanged, that you will return to the point of departure if we reduce nutrient inputs. That tenet is flawed. So, and we illustrated that with data. So I found some time series from 4 different sites that had all exposed to increasing nutrient inputs and decreasing. So you had this possibility to actually see what's happening when you increase nutrient inputs. In all cases, you would have a clear increase in chlorophyll concentration. But when you then started to decrease the nutrient inputs, then the system returned, but it did not return to the starting point. It all ended up with higher concentrations of chlorophyll. So this fundamental belief that was, you could say, underpinning the first action plan, that you can just reduce and then we'll get the same situation, that did not happen. We did a follow-up study in this a couple of years later. We're looking into 28 coastal ecosystems that were from 4 distinct regions. We had Chesapeake Bay, we had Danish estuaries, we had Tampa Bay, and we also had the Wadden Sea, some mainly Dutch data. We could see that most of all these areas, the 28, did not show a linear relationship between the lock of total nitrogen versus the lock of chlorophyll. Instead, many of them showed all kinds of trajectories, you could say, departing from linearity. And furthermore, when we looked at it, we could see that if you looked at the ratio between chlorophyll and TN, similar to what I showed before, we could see that there was an increase in time. So it's not just in Denmark you see this increase in chlorophyll over TN. So throughout many of the world's estuary, we see the same, that you get a higher chlorophyll yield for the same total nitrogen you have in the system. And this is a bit both puzzling but also worrying. Apparently, you could say our phytoplankton community is becoming a lot more efficient in terms of utilizing the nutrients. Another problem that's associated with eutrophication, that's hypoxia, especially if you have stratified waters. And we do have that in this part here, in this transitional area, where you have brackish water flowing up from the North Sea, and you have saline water coming in as a bottom current. This means that this area is permanently stratified, and that makes it very sensitive to hypoxia. What I've shown here, this is the latest report we have from about a month ago, and we know that it's always peaking in September. It's the worst month where it's most extensive hypoxia. This is showing how bad it was in the month of September. So if we start with the yellow shows area where the oxygen concentration at the bottom is less than 6 milligrams per liter. This is normally where you say the most sensitive fish, they start to migrate or move away from the area. In the orange, we can see this is where it's less than 4 milligrams per liter. At this point, most of the fishes have disappeared. They don't like anything less than 4. In the red one, this is less than 2 milligrams per liter. This is when it becomes really critical. In this case, when you're less than 2 milligrams per liter, a lot of the polychaetes, a lot of the other benthic fauna organisms, they die off, especially if this lasts for longer periods. And typically, this is something that is lasting for maybe 1, 2, 3, 4 months. So depending on where you are. So in many cases, we can have a strong, you could say, effect on the benthic fauna. I actually use an example because we had a survey in the worst year we've ever had in 2002, where we had 9,000 square kilometers affected by less than 2 milligrams per liter. We actually made a survey before and after on the benthic fauna, and we connected that to the exposure to low oxygen concentrations. And our estimate was that we lost about 300,000 tons of benthic biomass. So how much is 300,000 tons? And I say normally when I talk to people in the general public, it almost corresponds to the same weight as the entire Danish population. So it's just to put things into perspective. So we killed, you can say, biomass with a weight almost equivalent to all the humans that live in Denmark. Almost. Anyhow, if we look at the changes in the aerial extent of hypoxia, we can see this is the worst year ever. This was this very catastrophic 2002. But if we look at the development over the last 10 to 15 years, we can see that things have also gone wrong. You can say, despite that we are not changing the nutrient inputs, they have remained constant. Things are just going the wrong way. We have more, you could say, phytoplankton biomass, higher chlorophyll levels, and hypoxia is expanding again. That's a little bit concerning. Let me just show you just briefly how do we estimate the aerial extent, because all of these you could say aerial extent are based on discrete samples. So during the peak season of hypoxia, we send a ship out and we do a lot of profiling. But all these profiled are interpolated spatially. And we do that so for instance, we have a profile A and a profile B, which are connected here by some bathymetry here. This can be holes, etc. But we normally determine the different thresholds that we're interested in 4 milligrams and 2 milligrams per liter and 6 milligrams per liter, probably somewhere up here. Oh, right here, actually. So this is a profile where it ends at the bottom, but it's above the 4 milligrams per liter. But in this case, actually, we use a modeling approach. So looking at the profile in the last part of it, and we sort of project that down and say, if we'd had a deeper water column, we would have anticipated that with 4 milligrams per liter would have happened at this depth, and the 2 milligrams per liter would have happened at this depth. So we sort of, you could say, save, or you could say, use these depths for where we have the 4 milligrams and 2 milligrams per liter. And we get that from all the stations, those where it's observed in the water column and those where it has to be modeled based on the lowest part of the profile. It's just a technicality. But all of these are then using a spatial interpolation technique, are then used to create this shape of, or this oxycline that's describing at which depth is the 4 milligrams per liter located and at which depth is the 2 milligrams per liter. And then we combine that with the bathymetry. So that's the whole idea. Okay. So what are the factors controlling hypoxia? This is something that I think we've covered quite well. We already did a study that I did together with Daniel Conley. I was working on all the data here. And if we split it into the estuaries, we found that there were actually 2 governing factors for the oxygen concentrations or the oxygen conditions that we have there. One is the nitrogen input from land. So the more nitrogen input you have, the lower oxygen concentration you measure. And at the same time, we also looked at the wind speed in the summer period. So the higher wind speed, the more mixing and the more oxygen is being brought down to the bottom water. So it's basically just a balance between oxygen supply and oxygen consumption, where oxygen consumption is described by nitrogen input and oxygen, delivery or oxygen supply is governed by wind speed. For the Danish Strait, we found something almost similar. We found that nitrogen input was also important, and also we found that the inflow. So instead of, you could say, the wind, because in the open waters we have this permanent stratification. So not even the wind can break down that stratification. It's located at 15 meters and it's extremely strong. But on the other hand, what's important is actually opening the inflow or the movement of the bottom water. So the advective processes we have in the bottom layer. We had some model results on that, and that was also very significant. So that actually describes. So if you have a lot of, you could say, ventilation of the bottom waters, you have much better oxygen concentrations. Whereas if you have stagnant waters in the bottom water, it much more easily become depleted. And then finally, we found that temperature is an important thing. And temperature has two effects. Temperature is governing the amount of oxygen that's in the water when it starts as a surface current, and then it's brought down to the bottom water. So most of the water, the bottom water that we have, it's coming as, you could say, surface water from the North Sea that has a higher salinity, but then in the mixing between brackish water flowing out and North Sea water, more saline North Sea water flowing in, that surface water is brought down to the bottom, and depending on the temperature, it contains more or less oxygen. And the other thing is, of course, the respiration, how much of the organic matter is respired, depending on temperature. So if you have higher temperatures, more of the organic matter is being respired. This is just showing some examples of the seasonal. In the Danish Straits, we typically have a seasonal hypoxia. These are some different years, just showing that normally from, you can say, we have full saturation, oxygen being fully saturated in the bottom waters at the beginning of the year, but then after, after the spring bloom and over summer, you can say the oxygen concentration in the bottom water is just being more and more depleted, and it's down to, well, even zero, and in some cases we can have hydrogen sulfide. And then as the autumn storms and you say starts picking up again, and you have a lot more movement of the water, the oxygen concentrations go up again. This is opposed to the coastal waters. It's just exemplified with one estuary, where it can be much more dynamic. This is very much based on wind conditions. So you can have water coming in, you can have winds that are mixing down to the bottom, and then you have stratification reestablishing. And normally you have a very thin bottom layer, which means it doesn't take long stratification before the oxygen concentration is exhausted. We also have some historical data here. It's really great about working in the Baltic Sea, North Sea region is that not only do we have good monitoring programs, but we also have some historical data that actually show us something about what it looked like more than 100 years ago. These are oxygen concentrations, and these are bottom water, and these are from measured by Winkler titration. That has existed for more than 150 years now. And as you can see, these are just what I could, dig up from various archives and databases. So 100 years ago, there's one observation actually indicated we had hypoxic conditions, but overall, this was not an issue. We did not have any problems with hypoxia 100 years ago. You can also see that here in the 30s, this is where it starts, you could say, at least some observations start to have, you could say, oxygen problems. And this continues in the 50s and 60s. So this is all the data that I found, you could say, from 1900 up to 1970. After that, we have more continuous monitoring programs, and a lot more data to deal with. So from these data, I tried to estimate what was the aerial extent of hypoxia. And we could see here, these are the different colors that I used before, but relevant is the red and the orange one. This is where we have some problems that might be critical to fish and also to the benthic fauna. And this was not very widespread. It was really isolated in these entrenched areas here. And if we analyze the same data from the early 1900s, basically, there was no problem with hypoxia. Maybe just a little patch here, at least according to the model, that had less than 4 milligrams per liter when you estimate from the method here. So what are then the outlooks for hypoxia? So if we look at the data and we compare 2 different years, so we can look at 1998. This is work that I did again some time ago with Dan Conley. So we take 1 year where oxygen depletion or hypoxia was not an issue. This was a very, you could say, windy year, a lot of, you could say, water exchange, so it wasn't a problem. And then we had the catastrophic year. And the simulation that I did here was what would happen if the temperature of the water had been 4 degrees Celsius higher. Okay, in both cases, we would see an almost doubling of the area extent. So the red area here is the one that was hypoxic, and the blue one is how further it would have expanded if it'd been 4 degrees Celsius warmer. So temperature really has a significant effect on hypoxia. But then we could ask ourselves, what if we hadn't done nutrient management? And I use the same model again and say, okay, this is here, which was 2009. So in this case, we had about 3,000 square kilometers. This is in this case less than 4 milligrams per liter. But this is the estimate we have. But if we hadn't reduced nutrient inputs, our estimate would be that 7,000 square kilometers would have had less than 4 milligrams per liter. So this is something, and we did this also to clearly illustrate that the nutrient management reduction that we've had an effect. So if we hadn't done this, things would have been a lot worse than they actually were. So it was a good thing that we did a nutrient management plan. So, but it's not just about oxygen. It's not just about chlorophyll. There are also other consequences. And eelgrass is a very important thing. I think also in Shandong province, you have a lot of widespread meadows of eelgrass. I can say a lot of good things about eelgrass, but I think I'll say that for later. Anyhow, what we normally typically use as an indicator of what we measure is depth limit, because we know that with eutrophication, we have more phytoplankton and more organic material in the water column, and that attenuates light much more intensively. This means that less light is reaching the bottom, and you outshade aquatic plants like eelgrass. They are affected by eutrophication. And especially the deepest population are affected the most because there's no light coming down to them. So they cannot sustain growth any longer. But when we look at the changes over time, we can see that this is the maximum depth. So this is where you have the small patches of small shoots of eelgrass. Some of them might survive for the next year. In most cases, they don't. But you can say the full circle here that we have here, that's illustrating the main distribution. So this is where you have the dense meadows. So how far out do the dense meadows stretch? And as you can see in inner estuaries, they only go out to about maximum 3 meters. That's how deep they grow. In the outer estuaries, maybe 3.5. If you go out to the coastal waters, they might grow out to 5 meters typically. And then we have one estuary, which is a big one, which is Limfjord, which is only 2 meters. So, and if you look over time, basically there isn't much of a change. So despite that, at least in the beginning, there were some improvements in second depth, we didn't see any anticipated, you could say, outcome in eelgrass depth limits. There are some historical data again. I'll come back to them in a minute. But this is just a study showing what was the distribution of eelgrass in our waters for different periods. This is not really, it's not a true quantitative analysis that was done here, that was published by Christopher Boström, etc. They were looking more into like nostalgic or narratives of, you could say, eelgrass distributions. Around 1900, we have some very good data, and I'll show them in a minute. In 1933, this is from, it doesn't say so, but it should say up here, 1933, this is what they expected to be the eelgrass distribution. It was slightly reduced from what they had in this period here in the 1900s. So with this 30 years, there was a reduction. Then there was in the late 30s, we had something that was called the wasting disease. I don't know if that hit the eelgrass here in Shandong province, but the wasting disease is a virus, and it affected it killed large, you could say, populations of the eelgrass. And it's coming in, it's induced by a small marine snail. So this virus is coming in, it's sort of using it's a parasite or a virus that's using, say, this snail as a host. But this host does not like the lower salinities of the Baltic Sea water. So it was only affecting down to a limit like this, because here the salinity is lower. So it was not affecting all coast or all eelgrass meadows, but only the ones in the higher salinity areas. And then this one here is showing, you say, the more recent, or at least from 1994, what they had in this publication here. But there were some historical records, and around 1900, it was reported that eelgrass would typically grow to about 10 meters in the open waters and to about 5 meters in estuaries. And today what we see is 6 to 7 meters, maybe less than that in open waters when it's at best, and 3 to 4 meters in estuaries. Again, this is a place we have some really great historical. So more than 100 years ago, especially one marine scientist, his name was Østenfeld, Denmark, and these are all the green dots where he did some investigations, and it wasn't really harmonized. So he was using a rake to sort of take down a rake and find out were there any eelgrass at this depth, and they were measuring and say, okay, here the eelgrass is growing up to this depth. So he was actually identifying for all these spots what is the depth limit of eelgrass. This is actually a quite fantastic data set that allows us to tease out how deep did it grow. So this is over time. So this is from early 1900 to 2020. From his data in the open coast, almost 10 meters on average. And if we look at estuaries, around 5 meters. And this is how deep it grows nowadays. So you can see that clearly eutrophication over this more than 100-year period has a drastic effect. We can also see that on the second depths, we had much clearer waters 100 years ago, and this is not as clear any longer. This is the nitrogen input that I showed you before, again showing it peaked in the 80s, and then now we brought it down to a level which is much more like we had it in the past. But even though we've reduced the nutrient inputs drastically, a lot of things have not changed. And one of them being temperature. This is the summer temperature. This is not where we see the most drastic increase in temperature. This is actually happening in winter. But we can still see that over the last, you could say, decade, 2 or 3 decades, especially if you go from the 80s, etc., we have had an increase of about 2 degrees Celsius. It's becoming warmer. And then finally, we have another pressure factor when it comes to eelgrass, which is affecting our waters, and that's mussel dredging. So basically what we've been doing over time, I imagine is the same in China, coastal waters. We've been fishing down the food web. So we started taking out, you could say, the large fish, then the little bit smaller fish, etc. And at some point, there weren't any more fishes. So a lot of fishermen, at least some fishermen, coastal fishermen, would start fishing mussels. And that peaked here in the 90s. You really had an explosion in the amount of mussels. So typically blue mussels were dredged out of the sediments. And then that fisheries also, to some extent, at least, it didn't collapse entirely, but it just found a new plateau here where many of the estuaries are still being dredged for mussels. So together with my good colleague, Björn Carlsson, we looked at the data, and we also looked at the relationship between second depth and eelgrass depth limit. And this is the relationship, the black one, if we look at the historical data, where we have both depth limits and second depth. And then we also looked at contemporary data, and we have the sites or the estuaries where we don't have any trawling. And then we have the sites with mussel trawling, and we can see that the eelgrass depth limit, eelgrass does not grow out as deep as in estuaries where we have mussel dredging as it does in other estuaries. So clearly, mussel dredging has an effect. Even though they're not allowed to go in where the eelgrass meadows are, officially, they still do. So this led us to this conceptual diagram. That is, if we look at the relationship between second depth, or what is called water transparency, and eelgrass depth limit, when at deeper waters, you have this relationship. So if you have eutrophication, that will make the waters less clear, and that will reduce the eelgrass depth limit. If you have a trawling, that will have a more immediate effect, removing the deeper populations until a certain depth where the ships cannot go any lower. And then we have another effect also on eelgrass, and that's warming. And warming is affecting especially the shallow water populations. And the shallow waters you have, the more effective marine heat waves are. Because if you have like 1 meter, it doesn't take a lot of, you could say, a long period of warm weather to heat up that, you could say, 1 meter of water, as opposed to if you had 5 meters of water that needs to be heated up. So marine heat waves are a lot more you could say, affecting the shallowest populations of eelgrass. Another thing we're looking at, that's the macroalgae cover. We have monitoring of that. So what we measure is the cover of the macroalgae on, you could say, on suitable substrate. And this is a little bit, well, it's a little bit tricky here. So the whole idea is that you don't measure at the same depth, but we can, by looking at the relationship to depth, and there we formulate some different depth curves that normally have a peak somewhere in the immediate here. So there are some sites where we have low exposure. So in the beginning, at the shallow depth, the macroalgae are affected by wave action, etc. So they don't grow very good. But then they normally reach at some point a maximum extension or maximum coverage. And from then on, due to light regulation, the cover of macroalgae is just exponentially, more or less, just like light, the availability of light, it's decreasing exponentially with depth. And we use these models to allow us to actually to sort of combine data that's taken from different depths. Essentially, this is what is shown here in this diagram. Anyhow, this is probably one of the places where we've seen some positive effects. And we saw this positive effects in the beginning, where we also saw an improvement in the second depth, especially in inner estuaries. So here we've had it in outer estuaries, it's less pronounced. We also saw a little bit in coastal waters, and in the open waters, it's been more or less constant. So there are some improvements, at least there were in at least up to, you could say, around maybe 2010. We did a synthesis of all these data. And this is, yeah, it's almost 10 years ago that this one was published. Just to highlight, where do we start with this? All the investigations start, you could say, from 1990 as the base point. So if we look at the total nitrogen input, and these are smooth versions of the time series that were published in this one, but this is just synthesizing. So we had the TN input. This is this one, the dashed curve, and the TN concentration. They mirror each other quite well. So when you reduce nitrogen input, you also see a reduction in the total nitrogen concentration. And the same, to some extent, is also shown for the TN or TP input. So when you reduce phosphorus input, you also see a similar decrease in the concentration TP. At the same time, we saw a reduction in oxygen, and second depth in this period was more or less constant. But we've also seen another thing when we look at these data, that is that the stratification has increased over time. So one thing that we have noticed is that even though that, it's supposedly, some people say that the warmer temperature, you should get more energy in the weather, but we're seeing less and less winds. And a lot of it has to do, as I understand, I'm not a meteorologist or climatologist, but a lot of it has to do with melting of sea ice in the Arctic. So if you have less temperature difference, because if you have a lot of sea ice, then the air temperature can typically be -20, -30, -40 up there. If the sea ice is melted, you more or less have the same temperature as the water up there, around 0. This means that the temperature difference between mid-latitude and high-latitude air temperature is less, and that gives less energy and gives the wind condition, or reduces the wind conditions. So if we look at the other part here, so if we look at the chlorophyll level, we did see a decrease in the beginning up to like 2015. Unfortunately, in the last 10 years, it's gone the other way. So if we update this, we have to come up with some good explanations. This is for the biology. So we have here the eelgrass main depth, that has more or less been constant. We did see an improvement in the total cover of macroalgae. But another thing that's interesting is to look at the benthic fauna. I haven't talked about that yet. If we look at the biomass, there was a decrease in the total benthic biomass, which was consistent with the chlorophyll concentration, meaning that if you have less food available for the benthic fauna, you see a response in the biomass. But this response was not univocal. It was actually differing between the two types of, you could say benthic fauna we have. So we separated into filter feeders, which are the ones that filter the water column, typically mussels, bivalves, etc. And if you separate it into deposit feeders, we saw a strong increase in deposit feeders, and we saw a reduction in benthic filters over time. And this is related to what we have up here. This is the frequency of stratification that in this period that we analyzed in this paper was just increasing. So the waters would get more and more stratified. And when you stratify the waters, it's not an advantage for the filter feeders because they don't have access to the phytoplankton. Instead, the phytoplankton is just raining down as detritus, and then the deposit feeders will benefit from it. So this is a clear explanation to why did we see that change. So all of this allowed us to look at different recovery pathways. So the first one would be the first direct response. So nutrient load leads to reduced nutrient concentrations. The second pathway is that we have a little bit more diverse response in chlorophyll or the phytoplankton microalgae. That's also affecting the second depth. And this is affecting the filter feeders through some detritus. It should be maybe also something going down here. But we have this response, diverse response between deposit feeders and filter feeders, which is due to changes in the stratification pattern. So stratification is going up. This is negatively affecting the filter feeders. On the other hand, feeders are having an advantage of that. And then we have recovery, even more complex, that's involving the benthic vegetation. So we have a little bit of, you could say, improvement in macroalgae, but also stagnation in more recent years. And then we have eelgrass, which has basically shown no signs at all over the last 30 years or so. So going back to the paper, the Netherlands paper by Carlos Duarte and myself and others, we looked into different, you could say conceptual ways that these ecosystems can, different pathways they can take under eutrophication and oligotrophication. So here, the eutrophication would be the red one, and the green one would be the oligotrophication. This is what we term the return to Neverland. This is an illusion to think this is happening. This would be that basically the pathway going up and down is the same. We can have a regime shift, and a regime shift would happen if you have some kind of feedback mechanism. So, and we know that these are happening typically when, for instance, you have a hypoxia, then you have a lot more of nutrient being resuspended or being turned into the water column that's sustaining high productivity and maintaining things into a turbid regime. So we know that there are some theories about, and going into details about that, that can maintain a system in either a turbid or a clear water state. We also have shifting baselines. It's simply because nutrients is not the only pressure that we have in these systems. There are many other things that's affecting our coastal ecosystems. And if you combine them, shifting baseline, regime shift, you might have something that looks like this. You have going up this way, you have a nonlinear response going back, but you also end up in a very different position from where you came. So overall, if you synthesize it, there are a number of pressures. So in a country like ours, but maybe we can just say that this is also general. I'm illustrating this here with agriculture, and this is bringing out manure onto the field, but nutrient inputs is a major pressure. It's really something that's affecting our coastal waterways. Doesn't matter whether it's Denmark, China, anywhere else in the world. The more nutrients you put out, the more eutrophication you will have. We also have fisheries as an important factor. Not only is there a physical disturbance, like I saw it, or I mentioned it for the eelgrass, it's, if you have a bottom trawl going through an eelgrass meadow, imagine what's happening to the eelgrass after that. And another consequence of that is that you are completely altering the whole food web. So if you fish out all the big organisms, you are changing the functioning of the whole system. That also has a. And then we have climate change. This is really the dark horse of everything. Climate change is altering the system, its configuration is changing basically everything. Doesn't look too promising, does it? So definitely our coastal ecosystems are under significant pressure. And I think what we can manage, we should try to manage. We can manage, you could say, nutrient inputs, and we can manage fisheries. Climate change, I hope we can do it. I know that China is doing a very good effort to do it, and just understood that China now has more electricity being produced, or more, the energy from sustainable energy sources is now higher than, you could say, in fossil fuels, which is good. It's fantastic. I'm really pleased to see that China's leading the way there. So what are the conclusions? Well, nutrient concentrations, they follow nutrient reductions. That's obvious. That's a clear response. Phytoplankton does not respond linearly. It's a little bit more of a complex, and definitely climate change is somehow shifting that baseline. Exactly how does it? We still need to understand that more clearly. Oxygen concentrations, they depend on nutrient inputs, the physics, the ventilation, how often does it happen, what's the residence time of the bottom waters, and eelgrass that we have, it's far from the historical distributions that we have. It doesn't grow as deep as it did in the past, and it depends on light condition, the physical disturbance, and temperature. I put the temperature in with a question mark here because the average temperature does not have that much of an effect. There are a few studies that show that with, you could say, an increase in the mean temperature, because it's affecting respiration a little bit higher than productivity. Both, you could say, the primary productivity of eelgrass and respiration are affected by temperature. And the respiration is affected a little bit more by temperature than production of eelgrass. But the difference is subtle. So changes in the temperature overall will not have an effect. Instead, we have the marine heat waves, which a number of studies have suggested really can eradicate eelgrass meadows if you have these long periods of extremely high water temperatures. I've looked into our own data to see if I could find signs of that in Danish waters. I haven't found any smoking gun and say, here we have a marine heat wave that really the eelgrass. So, but it's been shown in other studies. And macroalgae, they respond primarily to light conditions, although that some perennial species are sensitive to warming. There are a number of reports that kelp species, they don't like the warmer conditions. What will come instead is always a question, because we realize that with everything, all the organisms we're looking, there's a poleward migration of species. That's happening everywhere. It's getting warmer everywhere. And species that have a temperature sensitivity need to move either further north in the northern hemisphere or further south in the southern hemisphere. So, and finally, it's not just about nutrients. We need to factor in all the other pressures that we're looking at and consider also fisheries, maybe also chemical inputs, and especially climate. And most of these pressures are operating synergistically. That means that if you have nutrient inputs and you have temperature, then the combined effect of that is even larger. So, and the relationships are complex and not predictable, not linear and predictable. So with this, I'll conclude my talk here, and I welcome any questions you might have on this. I hope I did not speak too fast. I hope it was understandable. So, look at it.
Thank you so much, Jacob. It's very interesting and very broad parameters and data sets.
Yeah.
I have a question about the chlorophyll A with the total nitrogen ratio. So you showed a slide with this ratio, but can you explain me why you use this ratio? What does it mean?
I'm not sure I understand.
What does the chlorophyll A?
Yes, oh, the ratio, the ratio
total
between,
nitrogen ratio.
so
Why
So
not total inorganic nitrogen?
So total inorganic nitrogen is a difficult variable to compare with chlorophyll because it's taken up by phytoplankton. So normally, if you take on a seasonal scale, for instance, you will see an inverse relationship between DIN and chlorophyll, simply because in the winter, DIN is building up because production is light limited. And in the summer, they take up, you could say, inorganic nitrogen. But both of them would be included in total nitrogen. So total nitrogen is a much better, you could say, measurement of the amount of nutrients or the eutrophication. So the understanding, and this is, so the relationship between chlorophyll and TN is not something universal at all. It also depends on, you could say, the bioavailability of the total nitrogen. You know that depending on where you are, if you have, for instance, if you have oceanic TN, you don't have much chlorophyll there because most of the TN there is inert. A lot of the total organic nitrogen is not really, you have a lot of DOM that contains nitrogen, but it cannot be used. It's not biologically available. So there you'd have a low ratio. In other places where you have a lot of, you could say, oil coming in, particularly if it's in coastal waters where a lot of the nitrogen is coming from land, you have a lot more of that nitrogen is available. So, but what we do here is that we're looking at time changes over time. So we are taking into account that different estuaries have different, you could say, signatures in the chlorophyll to TN profile. But if we combine all the trends together, then we get this, you could say, overall trend. So we are taking into account that that there are differences in the chlorophyll to TN between, depending on where you are, whether you're in open waters, whether you are in estuaries that are strongly influenced by land inputs. Mm-hmm.
For this question, what's the proportion of PN particulate nitrogen in total nitrogen? It's a lot from estuaries to the open.
It's changing a lot from it's higher in estuaries where you have more, you could say, biologically available nitrogen that can be converted into phytoplankton biomass. There is this gradient from, you could say, from land to the ocean. So the more you come out to the ocean, the higher proportion of the total nitrogen will be dissolved. So
even though you decrease the nutrients, even though the nutrients.
So my hypothesis and what I'm working on right now is that that with temperature increase, the turnover of nitrogen is increasing. So basically, you can imagine, imagine a wheel. A turnover is like a nitrogen molecule is used several times over a season. It's coming out from land, typically in winter. It's been utilized to produce, you could say, to sustain primary production, and then the phytoplankton, they die. The nutrients are being regenerated and then being reused for productivity again. But that recirculation or recycling of nitrogen is temperature dependent. So the higher temperature, the faster you could say that nitrogen molecule can be used again and again. This means that, just taking some numbers, in the past, it might have been that a nitrogen molecule was used 7 times throughout the season. Today, it might be used 10 times. And one thing you have to realize that every time it's been used, it too. And that produces, so you can say that going from, so like almost like use ratios and say, well, if you have nitrogen, you could say that's times. That is actually producing more or less 50% extra organic matter. I don't have the numbers. These numbers are just like taken out of the air, but this is my understanding of it. This is what's happening. This is that you actually, with temperature increase, the phytoplankton are becoming more efficient, especially also the whole recycling of nutrients.
Thank you, Jacob. Interesting talk. My question is about the we are not familiar with the current system in the coastal area of Denmark.
Yeah.
So my question is, how about the ages of the water mass in your area with long-term data when you compare from the 1990s to right now, the water exchange with the, for example, North Sea or Atlantic,
Yes.
is it changed a lot? Since nutrients maybe comes from the estuaries and the anthropogenic sources, another source maybe comes from the water exchange.
Yes. We don't have any exact numbers on you could say, like calculating the residence times of the water, but the modeling studies that we have show that in the Danish Strait, so the connection, the transition area between the Baltic Sea and the North Sea, typically the residence time is on the order of a few months.
Few months.
So we're not talking about like the Baltic Sea itself. The residence time is about 30 years in there. So that's a long system, but the transitional area is much different. There it's a few months.
So that is faster, much faster
Much
than
faster.
the Baltic Sea. Since I have I take a cruise in the Baltic Sea.
Yeah.
So I know that the hypoxia there is mostly caused by the exchange, the water, the long residence time of water mass, and the refresh or
Yes.
some like. So here is more faster. The water. I see your annual change
Yeah.
of your DO depletion. So
Yeah.
in the winter time, it can how to say
it's been
become
replenished.
replenished. Yeah, yeah. Oh,
Yeah.
so that
But yeah, I'll talk a lot more about the Baltic Sea tomorrow when I talk about oxygen.
so I since I don't know the currents here, so I don't know why it's just close by the two region. I think the story is quite different.
Mm.
But how can you explain the DO? You have some hypoxia. The trend is increasing, although the nitrogen load is decreased and the concentration is decreased. But the hypoxia, you have a trend.
Yeah.
It's increasing.
Yeah.
Why?
So what's, you could say, counteracting our nutrient efforts, and what has that is the main issue is the increasing temperature. So with
so the
increasing
stratification, you mean?
not a stratification, but two factors of oxygen, or sorry, of temperature on oxygen. One is that you have less solubility of oxygen in the water that has to come down, that feeds the bottom water. And at the same time, you have, with increasing temperature, you have higher respiration. So more of the organic matter that's been remineralized down in the bottom, you could say, or more of that has been remineralized with higher temperatures. And we always see that, you could say, the peak in September, that's where the highest, where we observe also the highest temperature in the bottom waters. And then, of course, also one thing that, but we haven't included that in models. That's, you know, what I just, we'll also talk about. You can say that you're getting from the same nutrient input, you're getting more biomass now, most likely. So that is also, this means that that will increase also the amount of organic loading to the sediments. So there are a number of things that are counteracting our efforts to actually improve the situation. But again, to repeat myself, if we hadn't already reduced the nutrient inputs, it would have looked a lot worse.
Thank you. Very good. Very nice talk. And since my research was mainly focused on greenhouse gases, so I'm really interested in your coastal water system.
Yeah.
Does anyone do research work about the greenhouse gases? So does the greenhouse gases respond to the change of this eutrophication, a long-term variation of all these different conditions?
So that is a very good question. And I don't think I have a clear answer to that. I don't think nobody has a clear answer to that. I think you're probably mostly interested in nitrous gas and also methane.
Yeah.
And a lot of that is, you could say, has to do, of course, with, you could say, the anoxic processes that you have in sediments. How that's changing, you know, I'm actually conducting a study that will take place next year. Shallow coastal region, greenhouse gas emissions, but more on understanding how you could say these shallow coastal systems, how they operate in terms of transforming inputs from land. But we will also have greenhouse gas. So hopefully I can give you a more exact answer on that in a couple of years from now. I think a lot of it has to do, of course, you could say with when it comes to nitrous gas, nitrous oxide, then that has to do with denitrification and denitrification. What's regulating that? That's still a mystery, I think. I don't think that anyone has. You have a very good idea of how come that in certain places you suddenly have more N2O being produced out of and less N2.
I asked this question because I have done some research work in the Aarhus University.
Yeah.
In China, in definition of Aarhus.
Yeah.
As you know, the nitrogen loading to Aarhus is decreased during the past maybe 15 or 20 years. I noticed that the emission of N2O is slightly decreased. So I'm still thinking about the response to the decreasing the loading of nitrogen. Or I just learned from you that maybe temperature, yeah, maybe because I only one of my master or my PhD students, they noticed when compared the his data with the dough, he found that it's we are still want to explore further. It's only when it comes to the decrease of nitrogen. It's really interesting.
It is, and I think there's still a lot of unsolved questions there, and I think what you need to compare is, has there been any changes in the ratio, or the total production of both N2 and N2O?
Yeah.
And is the proportion between those two, is that changing over time?
The ratio.
So if you look at if you look at the ratio between how much nitrous gas and nitrous oxide is being produced, is that constant over time, or do we see? Because you would probably have that if you have a reduction in nitrogen input, you would also have less denitrification, because you say denitrification depends on how much nitrate is available, essentially. But are you seeing shifts also in the balance between how much you say, if you look at the nitrogen pathways, how much is ending up as N2 and how much is ending up as N2O? I don't have the answer to that.
I think it's very complicated because for example, the bottom it's also shallow.
Yeah.
And maybe the nitrogen contribution process in the sediment will also influence the N2O, and also for the very shallow, the air change, a lot of different processes will influence.
And when it comes to something like methane, of course, that's salinity is very important there in regulating the methane production. So. Yeah, it is. But I think the amount of sulfate that can buffer the production of, you could say, of methane, that's, yeah. So, but one of the things that's interesting is also, what does it mean in terms of, you could say, if you have fluctuating salinity also for the sediments, and how much does that matter in terms of methane production? Yeah. A lot of things that, yeah, I don't have answers to that.
I have a couple of questions for your talk. You mentioned the hypoxia and the oxygen depletion. have you measured the sedimentary oxygen consumption? How maybe a few studies indicated oxygen was consumed in sediments.
Yeah.
So do you have some data
We
and compare the coupling of oxygen consumption in sediment and
we
near bottom water?
yeah, we do not have any like time series of sediment oxygen demand, SOD. We have some data that where we've taken, you could say, analyzed the fluxes of oxygen between sediment and water. But those are just for 2 distinct periods. We could compare those, but one of the problems of comparing, you could say, sediment oxygen demand is that it's extremely variable. You know, when you take a sediment core and you measure the oxygen flux between, you could say, surface and water, it's, you know, you take 5 cores and they give you 5 different results. And then if you take 5 cores in 1 year,